Hello and welcome. Today we're going to tackle a question that seems almost magical, but is at the heart of so much of our modern technology.
I mean, really think about it. How? We look at this picture and we just know. But a computer, it doesn't have eyes, it doesn't have a brain like ours, so how can it possibly identify this image with such amazing accuracy? Well, the secret is all about translation, turning what we see into a language that a machine can actually understand.
And right there, that's the first big clue. To a computer, this isn't a cute furry cat. It's data. It's just a massive, perfectly ordered list of numbers that represents every single pixel in the image. And to make any sense of that data, we have to start with the simplest question you can possibly ask. You see, before a computer can answer a big question like, what is this? It has to learn how to answer a much, much smaller one. Is this a cat? Yes or no? And this right here is a cornerstone concept in all of machine learning.
It's got a name, of course, binary classification. Binary because, there are only two choices. For us, the outcome is either a 1, meaning yes, it's a cat, or a 0, meaning nope, not a cat. And we call it a supervised task because we're basically the teacher. We're going to show the computer thousands of images that we've already labeled with the right answer. We're supervising its education.
And believe me, this isn't just for identifying cats. This simple yes or no logic is everywhere. Is this email spam or not? Is this credit card transaction fraudulent or not? Is this patient at risk for a disease or not? It is the quiet, powerful engine driving countless decisions every single second of every day.
Okay, so let's get down to the really cool part. How does a computer actually see this image? How does it perform that magic trick of turning pixels into numbers that it can work with?
So let's reset. Our main goal is to take an input, the picture of the cat, and train a machine to predict the correct output, which we're going to call Y. And Y can only be one of two things. 1 for cat, 0 for not cat. That's it. So here's how the computer breaks it down. Any color picture on your screen is just a mix of red, green, and blue light, right? Well, that means the computer doesn't see one single image. It actually sees 3 separate grids of numbers. There's one grid, or matrix, that holds the brightness value for the red in every single pixel. Then there's another one for green, and a third one for blue. Now, to get those 3 grids into one single input that the algorithm can use, we do this really clever thing. We take that entire grid of red pixel values, and we just unroll it into one super long column. Then we do the exact same thing for the green values, and stack them right underneath. And finally, we add all the blue values at the very bottom. And the result? Well, for a teeny tiny little 64 by 64 pixel image, you end up with a single list of 12,288 numbers. Yeah, that's 64 times 64 for the pixels, times 3 for the red, green, and blue channels. That is a ton of data for one little picture. In that giant list of numbers, that is the key to this whole thing. It has a special name. We call it the feature vector, and we usually represent it with a lowercase x. This single vector holds all the visual information from the original image. This is it. This is how the computer sees the cat. Okay, so we've got a handle on how to process one image, but that's not how neural networks learn, right? They learn from these massive data sets. We're talking thousands, maybe even millions of pictures. So how on earth do you organize all of that information? I mean, you can't just have millions of these separate lists of numbers floating around in your computer's memory. You need a super clean, really structured way to line up all your images and all their correct answers for the algorithm. And the solution is actually really elegant. We take every single one of those long feature vectors and we just stack them side by side as columns inside one gigantic matrix. We call this big one capital X. So the very first column is our first picture. The second column is our second picture, and so on, all the way to our last training example. And of course, we've got to do the same thing for the answers. We take the label for each picture, that 1 or 0, and we line them all up in a single row, which we call capital Y. Now notice this. The images are in columns, but the labels are in a row. This is so that the first image in matrix X lines up perfectly with its answer in row Y. Everything is perfectly aligned. But why columns for the images? Why not rows? Well, here's a little pro tip that comes straight from the experts. It turns out that when you're actually building these neural networks, using this very specific convention, images in columns just makes the math and the code you have to write way, way easier and more efficient. It's a small detail, but it's a standard practice that makes a huge difference. So, that was a lot. Let's just do a super quick review of the notation. This is the basic language we're going to use to talk about our data from now on.
All right, just lock this in. Lowercase x, that's the feature vector for just one image. Lowercase y, that's the label, the answer for that one image. M is just the total number of pictures we're training with. Capital X, that's our giant matrix with all the images as columns. And capital Y is the row with all their matching answers. Got it? That's the language of our data set.
And just like that, the really tedious part, getting the data ready, is done. We've taken this messy collection of real-world pictures and we've turned it into a perfectly organized, highly structured data set that a machine can finally start to learn from.
But that brings us to the real question, doesn't it? We have all the data perfectly organized, we have thousands of pictures and all the correct answers lined up. But how does an algorithm actually look at this gigantic matrix of numbers and start to learn the subtle patterns? The whiskers, the pointy ears, the shape of the eyes that just scream cat. Well, that is where the real magic happens. And that's exactly what we're going to get into next time.